Welcome everybody for the second in series of the Amal Raychaudhuri Memorial Lectures. This lecture series was initiated from a generous grant from Professor Ashok Sen, who was an Infosys professor here. He gave all his salary to set up this chair essentially during the COVID period. And subsequently several other people added to this fund, and together we set up this memorial lecture series. And the first one was given by Sunil Mukhi in 2023, and this is the second one. Today we have a very distinguished guest to deliver the second lecture, Professor Amitava Raychaudhuri of University of Calcutta. I would like to give you a brief biodata of him actually. Not full biodata, but a brief sketch actually. So Professor Raychaudhuri did his PhD from University of Maryland with O.W. Greenberg, and then subsequently he was postdocs at Oxford and TIFA, then later on at CERN and also at LBL, Lawrence Berkeley Laboratory actually. And he joined the faculty of University of Calcutta in 1980, I think. Is that right? I think 1980, right? And subsequently, he became the Palit professor at the University of Calcutta. And of course, he received several awards and everything. He was a director of HRI. He won the Bhatnagar Prize. He's a fellow of all the academies. And he's also a J.C. Bose fellow and various things essentially. He also had illustrious students, actually large number of students who are all faculty in many places in India, in most of the institutes and everything. Today he's going to talk about Neutrino novelties. So over to you actually. So yeah. Yeah. 1 second. We would like to present a souvenir to him. Please come actually, yes. For accepting our request and being present here and delivering this beautiful lecture. So, from IISc and everything. Yeah.
Thank you very much.
Yes. Yeah, this is heavy, so we take it. Okay, over to you. Actually, yes.
When I begin this talk, before I begin this talk, I have to say two reasons why I did not want to speak in this gathering. Firstly, of course, IISc is a place where there are extremely eminent people, and I have myself stopped doing research for a few years. So I was very hesitant to come and give this talk. Secondly, I do not, as a practice, I do not give a talk in the memory of my uncle, Professor Raychaudhuri. So as a practice, I don't do it. But, I must say that Dr. Sudhir Vempati, he was extremely, how shall I say, insistent, and I had agreed to him some time back. Now, to begin, Professor Raychaudhuri, I should say a few words about Professor Raychaudhuri. He had two aspects in his career. One was as a researcher, and the other was as a teacher. Now, for the researcher part, AKR did most of his research at the Indian Association for the Cultivation of Science. Now, in those days, and he came from, I would say, middle class family, it was very important that at every stage he had some financial support from some organization. So he was, after his MSc, he was looking for a research scholar position as jobs were not plentiful. It was not easy to get a job. And so after his MSc, AKR did get a funded research scholar position, and this was in, of all places, the X-ray laboratory, of the IACS. But at this time, he learned the general theory of relativity by self-study at the IACS library. The work for which he was hired, it didn't go very far, and then he lost his position. The funding went, basically, and so this project was not funded anymore. And so then he went to Ashutosh College, where he taught for a year and a half. Now at the Ashutosh College, he started writing papers on the general theory of relativity, and so then he obtained a permanent position at the IACS, a position called a research officer, and he got this permanent position after writing a few papers. Unfortunately, he did not get the support which he had expected from Professor Meghnad Saha. Professor Meghnad Saha was then the director of IACS, and he was instead asked to work in chemistry, and the director asked him to work in chemistry, which he did, in fact, but in parallel he pursued his interest in relativity. The work in chemistry, by the way, is cited. It's not something which is trivial. It got good citations. And then he wrote a DSc thesis, mostly on his papers on general theory of relativity, but also including his papers on chemistry. And he got a DSc degree, after which he got an offer of a professorship at the Presidency College. Then it was then a college, and he got an offer for a professorship at the Presidency College. Instead, at IACS, the director, who had heard about the glowing reports of Professor Raychaudhuri's thesis, one of his examiners was John Wheeler, so he knew about the good reports of his thesis, so he suggested that they should retain Professor Raychaudhuri and give him a promotion. And then this was discussed in a meeting, and where the other people, the other heads of the department said that in that case there are people in their groups who also deserve promotion, so that promotion was not granted, and so he moved to Presidency College. This is his paper on relativistic cosmology, in which the Raychaudhuri equation is derived. It basically has to do with the fact that he showed that just by introducing anisotropy in a model, one cannot get around to the problem of a singularity. That's the basic thrust of the model. But I do not want to get into the detail of that. And now AKR as a teacher, when AKR taught in the undergraduate and postgraduate classes, he taught the postgraduate classes in Calcutta University and also the undergraduate classes. He left a very lasting impact on his students. The students knew that he had done some high quality research, but it was very far beyond what they knew, and so they just only knew that he had done some good work. But what the students found of more interest was the originality of the ways in which the problems were being solved in the class. It was very original, and it inspired what I would call a false sense that physics research was easy. And his ever thoughtful nature, indifferent to what else is happening around, added to the mystique. And so, though not at all unfriendly, he was actually quite supportive of his students, but the students remained in great awe of Professor Raychaudhuri. Now I turn to the subject of today's lecture, namely neutrinos. And as you know, the neutrinos were suggested basically because the dog did not bark. That's the Conan Doyle story, Sherlock Holmes story. Why was that? That's because that if without the neutrino, we would have expected that the electron energy would be a unique fixed number. However, the electron energy showed a distribution, and this led Pauli to propose the existence of a neutrino. The neutrino conserves energy and also angular momentum. And another important method by which neutrinos are produced is pion decay. We'll come back to beta decay and pion decay later on. And as we know, neutrinos pass through the earth without interaction. It's very difficult to detect neutrinos, and that's the reason why it's also very harmless. There are three types of neutrinos. A new E is produces an electron through the weak interactions. A neutrino produces an electron, neutrino produces an electron, and then the other neutrinos produce the muon, the muon neutrino produces the muon, and the tau, the tau neutrino produces the tau lepton. Many of the properties of the neutrinos were discovered in the last decade. So in this talk, I would focus mainly on this third column. So here there are these are the fermions, and these are the bosons. The Higgs boson is a scalar particle. I have not included gravity in this slide. Now, the standard model describes the strong and electroweak interactions, and the standard model is mediated. There must be some force. There must be some force mediator which is exchanged, and the standard model forces are mediated by gluons, or the gluons for the strong interaction, and the W and the Z boson for the weak interaction, and the photon. Now, for fermions, there are left and right-handed quarks, left and right-handed charged leptons, and only left-handed neutrinos. Now, because there are only left-handed neutrinos and no right-handed neutrino is included, so therefore there is parity violation built in the theory. Now, I can give a very simple argument why without a right-handed neutrino, the neutrino would be massless. The reason is that for a fermion, there are two vectors. One is the momentum and the other is the spin. And if the momentum and the spin are parallel to each other, then we call it the right-handed neutrino. And if the momentum and the spin are opposite to each other, then we call it the left-handed neutrino. Now imagine that the neutrino has a non-zero mass. Now if it has a non-zero mass, then its velocity can be large, but it cannot be the velocity of light. So therefore, it is always possible to have a velocity, a frame moving with a velocity which is faster than that of the neutrino. So once you move faster than the neutrino, the momentum changes sign, but the spin does not. So therefore, left becomes a right. So therefore, a left-handed fermion can become a right-handed fermion in such a moving frame. Now, but that is the case if, of course, the neutrino is massive. If the neutrino is massless, then it always moves with the velocity of light, and therefore there is no frame in which you can go in which the momentum is reversed. So be that as it may, if there is no right-handed neutrino, the neutrino has to be massless. So the masses of the W, Z, the quarks and the leptons are all through the Higgs mechanism. However, there is no right-handed neutrino in the Standard Model, and therefore the neutrino is massless. This is chosen for consistency with information of that era. At that point, there was no reason to expect that the neutrino is massive. However, we now know that it is, in fact, it has a non-zero mass. Also, the lepton number and baryon number B minus L is a symmetry of the Standard Model. So one cannot say that the lepton number is violated and the neutrino can be its own antiparticle. I come back to that a little later. Now, so what are the neutrino interactions? There are two kinds of interactions, as I said. The weak interactions are mediated by the W and the Z bosons. The neutrino is uncharged and it doesn't have strong interactions, so those are out. So under a W boson interaction, a neutrino interacting with a neutron would go to an electron and a proton. But under neutral currents, a neutrino interacting with the proton will go to a neutrino and the proton. There is no charge change in this reaction. And similarly for the neutron. And this process, the neutral current process, is of the same strength for the electron or the muon or the tau. Now I have here Feynman diagrams showing how the neutrinos interact through the Z boson and how they interact through the W boson. So here is a cartoon. It says that, did you see anything? And the younger fellow says, no, nothing. And then the boss says, then it was a neutrino. If you don't see anything, then it is a neutrino. Now, there are ways to detect the neutrino, and I now come to two of the methods by which neutrinos were detected, one from the sun and the other from the atmosphere. The sun generates heat and light through fusion reactions, as we know. And the fusion reactions, 4 protons fuse to produce 4 helium, and then 2 positrons, and then 2 neutrinos, and 27 MeV of energy. And so just like sunlight, solar neutrinos are reaching us, but solar neutrinos reach us during the day as well as during the night, because as far as the Earth is concerned, it's transparent to neutrinos, so they can come. Now it's possible to make, of course, this process, the 4 protons cannot get together in one place to form this reaction. It's only the end product of a chain of reactions, and I don't want to get into the chain, but there is a robust prediction of the number of solar neutrinos reaching the Earth as a function of the energy. This can be it can be made. Such a robust prediction can be made. These have been detected by several experiments. However, there's a problem. Now here I show, for example, the different reactions, the PP chain. The PP reaction is the one which produces the maximum number of neutrinos. This is a log scale, so this is a huge number of neutrinos are produced, but these are of low energy. Of higher energy, for example, are these boron neutrinos or HEP neutrinos, which are of higher energy, but they are much less in number. Anyway, it's difficult to detect these neutrinos, and one of the first persons to measure the neutrinos from the sun was this Raymond Davis Jr. And what he did was he performed a very pioneering experiment in which neutrinos interacted with chlorine to form argon atoms and an electron, and then he managed to count the argon atoms because the argon was produced in a radioactive state. So he could count the number of argon atoms produced. And then what he observed is that the observed number of solar neutrinos over the expected number of solar neutrinos is only about a third. It's only about 1/3. So the first reaction was that Raymond Davis Jr. is a chemist, and the chemist has no business to do physics, and so he was ridiculed. But then several later experiments did some similar things, and they found shortfalls. The energy thresholds were different for various detectors. The other detectors used gallium or water, and so they had different thresholds, and the suppression was dependent on the neutrino energy. So this was a significant thing. The possibilities that were open at that point was, are neutrinos, electron neutrinos decaying on the way to the Earth, or are electron neutrinos oscillating to some other type on the way to the Earth? So these are the two questions. Now, an experiment that detects neutrinos of all flavors, not just electron neutrinos, but of all flavors, is the answer, because in this case, in the second case, if the neutrinos are oscillating, then there will be no change in such an experiment. But if the neutrinos are decaying, then the shortfall will just show up. So a similar experiment was run at the Snow Lab in Canada, and that uses neutral current interactions. And when that process, that measurement was made, then the observed number of neutrinos over the expected number of neutrinos was found to be 1, consistent with 1. So therefore it was clear that it's not a decay, but neutrinos are oscillating. Yes? They looked for disintegration of the deuteron. So what happens is that the neutron is absorbed later, and then it emits a photon of the characteristic energy. So it's a delayed photon emission, and they detect the proton. So that oh, because this was an unsolved problem. Because it was an unsolved problem, that one couldn't tell whether it was a decay or oscillations. He found the deficit. Yes. So the first step was in the detection of solar neutrinos, in which Davis succeeded. But Davis found too few. Let's detect solar neutrinos, and also to check the model, the solar models. So when the solar models, there were specific predictions. So when the predictions were not met, then other calculations were made, and those calculations agreed with the prediction, and yet there is this disagreement. So it was an open problem at that point, and that was solved by the Snow experiment. Now a similar thing is for the atmospheric neutrinos. What happens in atmospheric neutrinos is that neutrinos are produced in the atmosphere from pion and kaon decays. So let's look at the pion decay. A pion decays to a muon and a muon neutrino, and then the muon subsequently decays to an electron and its neutrino and muon neutrino. And also the charge conjugate process happens depending on whether you have pi minuses or pi pluses. Now the typical energy of the atmospheric neutrinos is much more. It's about 1 GeV or thereabouts, GeV scale. Now what we expect is that if neutrinos do not do anything funny, then we would expect that neutrinos from all angles should come equal in number. However, what was found is that the number of neutrinos, the number of nu mu, depends on the zenith angle. There is an up-down asymmetry, while there is no such variation for electron neutrinos. So you see here there are two diagrams. This one is for electron type neutrinos, and you see that the electron type neutrinos is completely symmetric, and it fits with the data very well. It fits with the expectation very well. Whereas in the muon neutrino case, there is some agreement here, but once the neutrino travels a long distance, this is when the neutrinos are coming from right through the Earth. When it comes over a long distance, then the number is fallen. Now this was again another way to determine that neutrinos are oscillating. Now of course here it's not that the electron neutrino is oscillating to something else, because the electron neutrino agrees with the expectation, but it's the muon neutrino which is oscillating to something else still, and so therefore we conclude that there are three types of neutrinos from this experiment. Now what are these neutrino oscillations? It's basically a very simple quantum mechanical phenomenon, and it relies on the superposition principle. In the oscillation of a pendulum, the bob alternately reaches one end point and then the other end point, and so on and so forth. Sudhir, please tell me 10 minutes before when it's time. So during travel, in this case, for the neutrinos, during travel an electron neutrino becomes a muon neutrino and then back again to an electron neutrino, and so on and so forth. This oscillation process continues. The oscillation wavelength, and this is a simple formula which we derive in the next slide, the oscillation wavelength and hence the probability depends on the neutrino energy. So it depends on the energy, it's proportional, the wavelength is proportional to the energy, and the wavelength is inversely proportional to delta, where delta is the mass difference between the two neutrinos. Now obviously if the mass difference is zero, there is no, the neutrinos are massless or they are degenerate, then the delta would be zero, and then the oscillation length would be, oscillation wavelength would be infinite, and we would not be able to detect any oscillation. So oscillations establish that neutrinos have a non-zero mass. So what is the physics behind this? The physics is simple. If I consider two neutrino states, then an electron neutrino is a superposition of the mass eigenstates nu1 and nu2. So it's this some linear superposition, and the muon neutrino is the orthogonal linear superposition. The mass eigenstates are the stationary states, where the flavor eigenstates, these states, the nu e and the nu mu, these are states which are produced and detected by the weak interactions. So the mass eigenstates are responsible for the propagation, and the weak eigenstates are for production and detection. Now oscillations between neutrinos, for example nu e and nu mu, is a consequence. It follows from this this flavor rotation, if you like, and the end result is that the probability of an electron neutrino going to a muon neutrino over a distance L, when it travels over a distance L, is 4 sine squared theta cosine squared theta, where these are the mixing angles, sine square pi L over lambda, sine square pi L over lambda, where lambda is the wavelength. The wavelength is determined by the delta, and sine theta has to be 0 or cos theta has to be 0 in order that this be non-zero. Yes, please. No, it's not propagating with the speed of light. It's massive. Yes, it's a good question. The point is that the neutrinos are not traveling with the speed of light, but it's nevertheless, the masses are so tiny that they are ultra relativistic. So therefore, to a good approximation, one can set that they travel with the velocity of light. But it is not exactly at the speed of light, it is less than the speed of light. But because the mass is very, very small, so it's traveling very fast. No. Yeah, was there another question? No, they are not oscillating between the E-type and the mu-type, because the E-type, the E-type agrees with observation. The E-type agrees with observation. So the mu-type is oscillating, and it must be oscillating to some third type of neutrino. So this is an evidence of 3 types of neutrinos. Okay, so let me go on. Now there is another significant thing which I have to develop, which I have to discuss, which has to do with the effect of interactions with matter. Now, as we know that mass is an effect of interactions. So neutrinos have weak interactions, the W and Z mediated. Now the Z mediated interactions, they affect all neutrinos in the same way. Now if all neutrinos are affected in the same way, then obviously that would not impact the neutrino oscillations. However, the W interactions with electrons only pick nu E, because you see only the neutrino of the electron type will interact with the electron in this way. That is, here the electron becomes a neutrino and the neutrino becomes an electron through a W exchange. Now, to understand what the effect of this interaction will be on neutrino masses, let's recall that in the ultra relativistic limit, what is important is 1 over 2e m1 square and m2 square in the diagonal. Why is this? Because if you expand p square plus m square square root, then the usual thing which we are familiar with is the non-relativistic limit, which is m plus p squared over 2m. M plus p squared over 2m. M is the rest mass, and then p squared over 2m is the kinetic energy. However, here we are in the ultra relativistic regime, so therefore when we expand, p is much larger than m, So therefore, the leading term is P, and then the next non-leading term is m squared over 2p. So the p cancels out, and I'm looking at now m squared over 2e. So this is the usual term for solar neutrino oscillations. Now I want to write this in the basis of the flavor, that is not the mass basis, but in the flavor basis. Now it's a simple thing to do because I have to make a transformation using the cosine and the sine, which we have written before. So once I do that, I get a leading term which is just this, and then a term which is proportional to the difference in the masses, delta m squared over 2e times minus cos 2 theta, sine 2 theta, sine 2 theta, and cos 2 theta. This is what we get in the normal case. Now when we include matter interactions, and we now include the matter interactions in the flavor basis, that is in this basis, where the flavor interactions, where the matter interactions are defined. So then there is one contribution from the Z exchange, but that is the same for all particles, all neutrinos. So that would simply contribute to the identity matrix, the one here. So that's simply an addition to this factor. And then there is an additional piece which I call 2a, and 2a is whatever is obtained from the W exchange factor times a factor of 2e over m squared, delta m squared, which I factor out because of this factor sitting in the front. Now once I include all of that, the effect of matter is that there is one term which is proportional to the identity, which does not take part in oscillations, and then the remaining part is just this. Now this I have to compare with whatever was there in the flavor basis in the absence of matter interactions. Now when I compare these two, I notice the following, that here this matrix has a determinant of -1. This matrix does not have a determinant of -1, but it has something else. It has a determinant of x. So in order to make it into a matrix of determinant 1, this should be 2 theta. In order to make it into a matrix of determinant -1, I have to pull out a certain factor x, so that would affect the delta m square. So I would have delta m square matter is delta m square times x, and sine square 2 theta matter is sine 2 theta. Sine 2 theta matter is sine 2 theta over x, where x is this, which is the determinant of this matrix. Now, of course, here I have assumed that it's a matter of uniform density, but of course, in the sun, for example, this is not the case. The density varies, so one has to take into account how the density varies over the radius of the sun. And then also when the density changes, one has to assume that the situation is adiabatic, which means that the system has time to become an eigenstate of the Hamiltonian. So those assumptions I have made, but I have not made them explicit. Now, be that as it may, the important fact is that for the solar neutrinos, what we now know is not just m2 square minus m1 square, but we also know its sign. That is to say, we know that m2 square is larger than m1 square. That is because in the sun, the matter effect is important, and the matter effect determines the sign of delta m square. However, from atmospheric neutrinos, where we see neutrinos coming through the Earth, there is no measurement of the charge of the neutrino. So the charge of the muon produced from the neutrino. So therefore, we only know the magnitude of m3 square minus m1 square. This is known, but we don't know the sign of this quantity. So therefore, there are two options: either the normal hierarchy, in which case nu1 and nu2 are close to each other and nu3 is higher, or nu1 and nu2 remain close to each other and nu3 is lower. The splitting between nu1 and nu2 is fixed by the solar neutrino problem. It's only the atmospheric neutrino problem which does not fix the sign of the mass splitting, and therefore we don't know the details. Now, of course, when we have three flavors of neutrinos, yes? Yes, it includes the possibility that one of the neutrinos is massless. Yes, it does. Yes. Now, instead of two flavor mixing, in which case we had a 2 by 2 matrix, in reality there are three flavors. So there are three angles and one phase. It's like the Euler angles that we are familiar with. And so the three angles and one phase. So this the phase is a signal of CP non-conservation. Now there is an industry to fit the neutrino mixing angles, the three angles and the phase and the mass splitting. It's a major industry, and of course we do not know whether there is normal hierarchy or inverted hierarchy. We don't know that. So there are two possibilities. Now if you look, the two possibilities are generally rather close. However, they differ vastly in delta Cp. If it is normal ordering, then the delta Cp is consistent with pi. Now if the delta Cp is pi, then there is no Cp violation. On the other hand, in the inverted case, delta Cp is consistent with 270 degrees, which means that it's strongly violated. So it would be good to know whether it is normally ordered or inverted ordering. Now what are the unknowns? The unknowns are, is the mass ordering normal or is it inverted? Theta 3 is very close to pi by 4, but not quite. It is in the first octant. Is it in the first octant or in the second octant? This is unknown at the moment. And what is the value of delta Cp? Now, still we do not know these answers to these questions. There is a problem in fitting data. There are degeneracies, and multiple solutions can give rise to multiple solutions can fit the data. For example, we saw the Cp phase can be very different in the two cases of inverted and normal ordering. So several ongoing experiments are trying to throw light on these issues. Now here I show the different types of neutrino sources. I will stick to only 4 kinds. The solar neutrinos, where fusion reactions take place and the energy of the neutrinos is a few MeV. Atmospheric neutrinos, which come about because of pion decay or kaon decay, and that has energies of the order of a GeV, that is 1000 times. And reactor antineutrinos, which are fission reactions, and that again tells us that a few MeV of the energy for the reactor antineutrinos. And then accelerator neutrinos, which are long baseline, and they again come from pion decay, and typical energies are GeV. So what are the experiments which are going on at the moment? Now the solar neutrinos, these are the pioneering Davis experiment, and then various other experiments which have been carried out, some still going on, and these are the oscillation pioneers. The atmospheric neutrino experiment, the baselines range from 0 to the diameter of the Earth, and E is a GeV. Now remember, the important factor is L over E. So it's L over E which determines what delta M square we can probe in the experiment. Now for the atmospheric neutrinos, the L varies over a range of let's say 10,000 kilometers, and E is a GeV. Here the energy is an MeV, but it's coming from the sun. Here in the reactor neutrinos, E is a few MeV. Now it's convenient for reactor antineutrinos to detect two things. One is to determine theta 1,3, one of the mixing angles, and that is for that one requires a baseline of about 1 kilometer. Another thing which is an open problem is the existence of a possible sterile neutrino, because there are some experiments which have claimed that they have seen oscillations to a fourth neutrino state, but we know that there cannot be a fourth light neutrino from various experiments. So therefore that must be a sterile neutrino, and to look for a sterile neutrino of the electron volt scale, one requires a baseline of 10 meters or thereabouts. So this is 1 kilometer, this is 10 meters. Theta 1,3 was extracted by several experiments, and in China a bigger reactor experiment, Juno, is being designed, is being set up. Now I quickly run through the remaining ones, the accelerator neutrinos. Now here we have a copious source of nu mu, because it's from pion decay, so it's nu mu which of GeV neutrinos from pion decay. Both muon neutrinos and antineutrinos can be produced depending on the charge of the initial pion. Now this is ideal for long baseline experiments because you have a targeted beam, and you can point it to the Earth basically, and then it surfaces after traveling from maybe several hundred kilometers to 800 kilometers. So several already completed at CERN and Fermilab, and the ongoing experiments are in T2K and NOVA. I'm sorry I don't go into the details of this, and future Dune experiment is being planned, and from Fermilab, and Hyper Kamiokande from Tokai. I would now want to ask the question, what about neutrino masses? How do you determine the neutrino mass? Now the first question which we can ask is whether the neutrino is a Majorana particle. Now if the neutrino is a Majorana particle, then it is its own antiparticle. Now, this is not a very unnatural thing. The photon is its own antiparticle. The pi 0 is its own antiparticle. So we know bosons, which are antiparticles of themselves. So it's possible that the neutrino is its own antiparticle. So in such an event, lepton number is of course not conserved. If the particle is its own antiparticle, lepton number is not conserved. Now, a consequence of this would be neutrino-less double beta decay. Now, what is a neutrino-less double beta decay? Normally, you have a process, a double beta decay process is a process where you have 2 electrons and 2 neutrinos. But here, the 2 neutrinos basically kill each other, and you just have 2 electrons in the final state. Now I go back to the previous slide where I had shown Pauli's picture. Now, Pauli had proposed that the neutrino is there because what was his answer? His answer was the conservation of energy, that otherwise the electron would have unique energy. Now, if there is neutrino-less double beta decay, then there is no missing energy. So the sum of the electron energies must be exactly equal to the difference of the masses of x and y. So look for a peak in the 2 electron total energy. That would be the answer whether we have neutrino-less double beta decay or not. Now the double beta decay is proportional to m nu square. So it's a highly suppressed process, and the current limit is m nu is less than 0.2 electron volt, and there are many ongoing experiments using different nuclei which are being tried to answer this question. Now, besides this, there was this question that whether it's possible for the neutrino, one of the neutrino masses to be 0. Now, what is the absolute scale of the neutrino mass? Now, for the other neutrinos, it's difficult for us to measure, but for the electron neutrino, this is produced in beta decay. Beta decay actually produces antineutrinos. And so a way to obtain the neutrino mass can be through a careful examination of the beta decay endpoint spectrum for the electron energy. So what you do is you look at the endpoint spectrum and see whether the Courier plot is sharp or not. And this precision spectroscopy of the kinematic endpoint of tritium beta decay gives the result that m nu is less than 0.45 electron volts at 90% confidence level. This is the Catherine experiment, which is the most recent experiment that has done this result. Now, after all this, we would like to still ask the theory question, how to get a very small neutrino mass. Now, the mundane way is to add a right-handed neutrino to the standard model, and then you write down a mass term, just like you have written the mass terms for all the other fields. So using the right-handed neutrino, you can write a mass term. This solves the problem, but has no explanation for the smallness of the neutrino mass. So you have to artificially take the y to be very, very small, and then one has to explain why is small. This is a major hurdle in neutrino model building, and to explain the smallness, one always needs new physics associated with some heavy scale, and so there's some kind of seesaw. So the neutrino mass is small because there's some heavy mass in the theory. Now, there are various models in which such ideas have been explored, and one of them, the one which is very popular is Weinberg operator for and seesaw masses. If the neutrino is of the Majorana type, then lepton number is not conserved. So there's the possibility of leptogenesis, and Weinberg wrote down this operator where m nu is some heavy mass scale which is the seesaw mass scale, which suppresses the neutrino mass, and it has 2 of the leptons and 2 Higgs doublets. Now there are various variants of the seesaw. There's a type 1 model where the exchange particle is a right-handed neutrino, which is a singlet. Then there is a type 3 model where the right-handed neutrino is an SU2 triplet, 3 right-handed triplet, and then there's a type 2 model where there is a triplet scalar. There are various models. I don't go into the details of these models, but this is one way in which it is possible to get a suppression. Then there are variants of this. For example, the inverse seesaw, where one incorporates not only the right-handed neutrinos, but also a singlet neutrino mu, which has a Majorana mass. And if the mu is small, then the mass of the neutrino is suppressed. So of course, the question then passes on, why is the mass of mu small? Then there are various arguments which have been advanced why the neutrino mass could be small. There are other seesaw variants and texture zeros and so on, which I don't want to go into. But there's another model where the suppression or part of the suppression comes from the factor 1 by 16 pi square, which comes in any loop diagram. So for any n loop diagram, the suppression is 1 by 16 pi square to the n. Now I give the simplest model, the scotogenic model of Ma, and in the scotogenic model there are 2 new particles which are introduced, the right-handed neutrinos Nk and the scalar particle eta, which are both odd under Z2. So if Z2 is unbroken, then this provides a dark matter candidate, and the one loop diagram has the 16 pi square suppression, and then various other factors which can be calculated. Now there are various other possibilities, for example, left-right symmetry that provides a natural room for the right-handed neutrino. The left-right symmetric model has a left-handed doublet and a right-handed doublet as well. And so the right-handed neutrino is already included in the model. It has different, it also includes within its scalar multiplets a triplet scalar which can give rise to a type 2 mass of the neutrino. So type 1 and type 2 can both be included here. Now a similar idea is the GUT model, the Grand Unified Theory model. For example, SO10 GUTS provides a natural framework for inclusion of left-right symmetry through the Pati-Salam SU4 color cross SU2 left cross SU2 right root. So here again, just as in the previous model, the left and the right multiplets are there. The right-handed neutrino is included in the 16-plet, the fundamental representation of SO10, the simplest representation, and then quark-lepton unification says that the 16 includes 421 and 412, and these various, the triplet Higgs is also included. The stepwise symmetry provides the required high scales, and of course one must remember that the proton decay bound has to be satisfied. So I come, before I was going to say I come to the end of the talk, but before I come to the end of the talk, there's this other thing, the neutrino nucleus coherent scattering experiments. Now this is a new phenomenon, and where the basic goal is that normally we consider neutrino scattering of electrons or perhaps quarks, but in neutrino nucleus elastic scattering, it is somewhat like the dark matter technique. Here neutrinos scatter coherently off nuclei, scattering mediated by Z boson exchange, and the energy must be very low. So because the energy is low, so the nucleus feels like a whole thing. This is a very important new method which is entering neutrino physics, but I would not like to elaborate on that. Now, in summary, what I have said about, what I've talked about, the solar reactor and accelerator oscillation results give information on neutrino mass and mixing. However, we still don't know whether the neutrino is a Dirac particle or a Majorana particle, whether it's its own antiparticle. There are many ongoing experiments. I have listed some of them, but not all. Various models of small neutrino masses and mixings exist. For example, modular symmetry, anarchy, higher loops, etc. I do not discuss all of them. Seesaw is a popular direction. Many other ideas like supersymmetry, in which Prof. Empathy made fundamental contributions very early, then extra dimensions and so on. Then an early determination of theta 2-3 mass ordering and CP violation will considerably narrow down our options, because right now we have too many open options available. But neutrino mass, what we want is not just mass splitting, but we want to know the absolute neutrino mass scale. Supernova neutrinos, something which I left without discussing. Astrophysical and cosmological implications, and actually bounds on neutrino masses. Some of the neutrino masses come from cosmology, then sterile neutrinos, and then possibly geophysical applications. Now, I've given you a lecture on quarks, neutrinos, mesons, and so on. Now, these are all those damn particles you can't see. That's what drove me to drink. So this is the person sitting in the pavement, and this is the person who's asking. And he says, now I can see them, the one in the pavement. Now, I'm not advocating that you take to drink. What I'm advocating is that much work is needed in particle physics. Thank you.